And the final example is example number 13. And 13 is the number of the greatest Gaelic footballer ever, in my opinion, Matt Connor. Okay, so let's look at the question. A hollow shaft having external internal diameters of 88 millimeters and 50 millimeters respectively transmits 1.5 megawatts at 2000 RPM. The shaft is connected to another shaft by a flanged coupling having 8 bolts on a pitch circle of 180 millimeter diameter. We're asked to determine the maximum permissible diameter of the bolts if the shear stress is not to exceed 50 meganewtons per meter squared. We're also asked to calculate the maximum shear stress in the shaft. So let's look at the question again, this time using a figure to help us. So we're told that the shaft has an internal diameter of 50 millimeters and external diameter of 88 millimeters. It transmits 1.5 megawatts at an RPM of 2000. The shaft, so this shaft here, is connected to another shaft by a flanged coupling. Okay, so this is the flanged coupling here and here. There's the bolts, and we're told that there are 8 bolts on a pitch circle of 180 millimeters. So that tells me that the distance from there, the center of that bolt to the center of this bolt, is 180 millimeters. And we're asked to calculate the max diameter of the bolts if the shear stress is not to exceed 50 meganewtons per meter squared. Okay, so we have all our information. These are the standard formulae. So let's just substitute in with what we know. So we know N is 2000. So I can work out what omega is, and omega works out to be 209 radians per second. I have the inside diameter of 50 millimeters and an outside diameter of 88 millimeters. So that gives me a second polar moment of 5.27 by 10 to the power minus 6 meters to the power 4. I'm told the power is 1.5 megawatts. We just calculated the radians per second to be 209, so therefore the torque is 7,177 Newton meters. Okay. So if that torque is applied here, it's the same torque is going to be all along the shaft. So that means the torque out here is also going to be 7,177 Newton meters. But we know that torque is forced by radius. And this radius here is half the 180 millimeters, so it's 90 millimeters. So we have a force, some force acting at 90 millimeters from the center of this flange to give us a torque of 7,177 Newton meters. So torque is forced by radius, so the force is torque over the radius. So that's 7,177 Newton meters divided by the radius, which is 90 millimeters, and that gives me a torque of 79,744 newtons. There are 8 bolts, so the force on each bolt will be 1/8 of the 79,744. And that works out to be 9,968 newtons. So each bolt has a force of 9,968 newtons on it. Shear force, I should say. Okay, so shear stress is force over area. So the area of the bolt will be the shear force divided by the shear stress. The force is 9,968, and the question told us that the shear stress was to be limited to 50 meganewtons per meter squared. However, the bolt, even though it has a hex head, the bolt part is circular. And we know that the cross-sectional area of a circle is pi r squared. So I know that pi r squared is equal to 9,968 all over 50 meganewtons per meter squared. And I can then get a value for r squared and and get the square root of that. Gives me R, and that works out to be 8 millimeters, or the diameter of the bolt is twice that, so it's 16 millimeters. Okay, so that's the minimum diameter of the bolts. What was the second part? Well, the second part of the question then was to calculate the maximum shear stress in the shaft. Well, shear stress, tau, is equal to T over J, all over D over 2. So I'll just substitute in my values for T and J. So T was 7177, and J was 5.27 by 10 to the power minus 6. And D over 2, well, the radius, we use the outside diameter, which is 0.88. That should be 0.088. All over 2. Okay, so I'm just going to put those values into my calculator. So it's 7177 multiplied by 0.088 all over 2. And that's 5.27 by 10 to the power minus 6. And that is 59 so 59.9 by 10 to the power 6, which is effectively 60 meganewtons per meter squared. And that's it.